This lesson is on Earth's interior. What is inside Earth? That is a great question. I would imagine quite a few people have different answers for this as to what might be inside or what they might think is inside Earth's interior. As you know, Earth is thousands of kilometers thick. The deepest mines and wells in the world barely scratch Earth's surface. So how do you think that scientists learn about Earth's interior? As you take a look at the picture on the left-hand side, the explorers in the picture look tiny as they descend into the cave at Mystery Falls, Tennessee. Mystery Falls is the deepest cave in Tennessee, which drops almost 86 meters, which is half a mile down. Although this seems deep, it is far above the center of Earth, which is 6,300 kilometers below the surface, or roughly 3,900 miles. As we go through the information in this text about Earth's interior, I want you to remember several things so that we can talk about them, and that are key concept questions. Our key concept questions are very important because these are the key items that we need to know for you to be successful at this lesson. One of the key concept questions that I would have is, what are the interior layers of Earth? We will be going through this information in this lesson, so please pay attention and write the information down in your science journal when we go through it. Another key concept question would be, what evidence indicates that Earth has a solid inner core and a liquid outer core? This information is quite important, and throughout this lesson, you will learn this information. Some other things that you're going to make sure you need to know, and I'm quite sure that you understand that these are important, and that is our vocabulary words. Throughout this lesson, we will talk about several things, one of them being crust, the definition of crust. Mantle will be another one. Lithosphere. We will talk about asthenosphere. We will talk about core and magnetosphere. These 6 terms need to be written in your science journal, and as we go through the information, you need to write the information down that will define these terms so that you have them to study from. Clues to Earth's interior. Were you ever given a gift and had to wait to open it? Maybe you tried to figure out what was inside by tapping on it or shaking it. Using methods such as these, you might have been able to determine what was inside that gift. Scientists can't see what's inside Earth, but they can use indirect methods such as the same ones you use by tapping or shaking on your present to figure out what it was, for scientists to determine Earth's interior and what it is like. What's below Earth's surface? Deep mines and wells give scientists hints about Earth's interior. The deepest mine ever constructed is a gold mine in South Africa. It's about 3 kilometers deep. People can go down the mine to explore the geosphere and see how the interior of Earth looks. But another one that was drilled was a well, and they drilled wells even deeper than the mines go. The deepest well is on the Koala Peninsula in Russia. It's more than 12 kilometers deep, about 7 miles or so, and drilling to such great depths is extremely difficult. It took more than 20 years to drill the Koala well. Even though people cannot go down inside the well, they can use instruments by sending them down into the hole to make observations and bring samples back to the surface. So my question to you would be, what have scientists learned about Earth's interior by studying mines and wells like the ones mentioned just a second ago? As we go through the material, if a question is posed on the screen, I'd like for you to go ahead and write it down in your science journal and try to answer that question so that we can discuss it in class the next day or when we discuss the information. In this case, I have 3 questions for you that I would like to have in your science journal and have them answered. The first one is, what do you expect the conditions to be at Earth's core? And what kind of material would be found there? Again, what do you expect the conditions would be at Earth's core? And what kind of material would be found there? The next question is, have humans ever collected samples of Earth's core, and why? Have humans ever collected samples of Earth's core, and why? Another question would be, do you think a cave is likely to be several kilometers deep or hundreds of kilometers deep? Do you think a cave is likely to be several kilometers deep or hundreds of kilometers deep? Those are the questions I'd like for you to have written in your science journal, and also have answers to them, at least your thoughts written down. One thing that workers notice in deep mines and wells is that it is hot inside Earth. No one has ever recorded the temperature of Earth's center, but it is estimated to be about 6,000, that's 1,000 degrees Celsius, which is about 11,000 degrees Fahrenheit. I know that the temperature at the bottom of the Koala well in Russia is about 374 degrees, which is hot enough to bake cookies. So they could bake cookies in that well because of the depth. Temperature within Earth increases as depth increases. So I'm going to show you the chart over here to the left. The top chart happens to do with depth. The bottom numbers is an increasing in depth. So the farther down in the well you go, it'll show you that the temperatures, which is on the left-hand side, the temperatures increase. So the farther down, the more the temperature, or the hotter the temperature, as indicated by the green line. Not only does temperatures increase, but pressure also increases as depth increases inside Earth. This is due to the weight of the overlying rocks. The high pressure squeezes the rocks and makes them much denser than the surface rocks. So if you look down here in this chart, you're also looking at depth at the bottom, and to the left, you're looking at pressure at atmospheres, million atmospheres, and that is to the left. You will notice the orange line increases as the depth increases. So that means pressure, which is here, increases as depth increases. So both temperature and pressure increase the farther down into Earth's surface you go. The high temperature and pressure make it difficult to drill deep wells, or even for any scientist to determine what is any deeper than what some of the wells that have already been drilled. The depth of the Koala well is less than 1% of the distance to Earth's center. Therefore, only a small portion of the geosphere has been sampled. So the question would be, how can scientists learn about what is below the deepest wells? Now remember earlier we talked about indirect methods of learning things, and so in this case one of the indirect methods that scientists might use to study Earth's interior would be earthquake waves. They get most of their evidence by analyzing earthquake waves. Earthquakes release energy in the form of about 3 types of waves. As these waves move through Earth, they are affected by the different materials they travel through. Some waves cannot travel through certain materials. Other waves change direction when they reach certain materials. And by studying how the waves move, scientists are able to infer or guess, make an educated guess, about the density and composition of the materials within inside Earth. Remember that differences in density result in materials within Earth forming layers. Each layer has a different composition, or what it's made up of, with the densest materials in the center of Earth. They move to the center of Earth due to gravity. The brittle, rocky outer layer of Earth is called the crust. Remember, we talked about those terms that you need to remember, and crust is one of those terms. I'm putting the information out so that you can write your definition. Please do so in your science journal so that you have the definition of crust. It will be one that is going to be required for you to have. The brittle, rocky outer layer of Earth is called crust. It is much thinner than the other layers, like the shell on a hard-boiled egg. It's very, very thin. It is the least dense layer of the geosphere, which means it's the one that's pushed towards the outer portion. It lies on top because it's least dense. It is made mostly of silicon and oxygen. Crustal rocks are under oceans and on the land. So as I show you here, you will notice that we have both oceanic crust, which is this right here, as well as continental crust, which is this right here. The crust under the oceans is called oceanic crust. It's made mostly of dense rocks of iron and magnesium. The crust on the land is called continental crust. It is about 4 times thicker than oceanic crust. The continental crust is thicker under the tallest mountains. It's made up of iron and magnesium. There is a distinct boundary between the crust and the next layer underneath of it. When earthquake waves cross those boundaries, they speed up. That indicates that the lower layer is denser than the crust. Now we're going to be talking about the mantle. Earth's mantle is immediately below the crust. The mantle is the thick middle layer in the solid part of Earth. That happens to be one of our vocabulary words, so I'm putting it on the screen now for you to write your definition in your science journal. Thick middle layer in the solid part of Earth is called the mantle. It contains more iron and magnesium than the oceanic crust does, and this makes it denser than either types of crust. Denser means that it will sit or push it below because it is more dense. So it's below the crust, both crusts, oceanic and continental. Scientists group the mantle into 4 layers according to the way rocks react to the forces pushing or pulling on them. I'm going to go ahead and open this back up and give you some information in reference to the layers. The first type of layer would be the uppermost mantle. As you can see, that's right here. The uppermost mantle lies directly below the oceanic crust and the continental crust. The rocks in the uppermost layer of the mantle are brittle and rigid. Brittle means they break easily. Rigid means they're very firm. Like the rocks in the crust, they just exactly like that. They're brittle, but they're rigid, very firm. Because of this, scientists group the crust and the uppermost mantle into a rigid layer called the lithosphere. I'm going to go ahead and shrink this back down again. Shrinking this one and giving you the next definition, which is that of the lithosphere. Please write that in your science journal. The lithosphere, again, is the crust and the uppermost mantle. They form together a rigid layer, which is called the lithosphere. Okay, I'm going to close that back down. Give you your information back again. The next layer, or the layer below the lithosphere, are rocks that are so hot that tiny bits of them melt. When this happens, the rocks are no longer brittle. They no longer break. They begin to flow or move. Scientists use the term plastic to describe rocks that flow in this way. This plastic layer within the mantle is called the asthenosphere. As you see right here, this is the asthenosphere. Okay. The word plastic, as I refer to it, means the material is soft enough to flow. The asthenosphere flows very slowly. Matter of fact, the rocks in the asthenosphere move about as slow as your fingernails grow, which means if you were able to see the rocks in the asthenosphere, which you're not because of the intense heat, you wouldn't notice them moving at all. You wouldn't notice them flowing at all. So again, I'm going to go ahead and close this down and pull up our next vocabulary word, which is asthenosphere. It's a plastic-like layer within the mantle. Okay, that plastic-like layer isn't like plastic we know. It refers to the material that is soft enough to flow. Okay, so plastic as we know it is not soft enough to flow, but the plastic in this case, what they're talking about is soft enough to flow. Okay, I'm going to move that back up again. And the last of the mantle layers is the rock that's below the asthenosphere, which is solid, but it is hotter than the rocks in the asthenosphere. Now, you may say, okay, that's weird because the asthenosphere's rocks are very hot and they flow or they move or grow. However, the pressure at the depth where the upper mantle and the lower mantle are is so great that no melting occurs. So it doesn't melt the rocks. The heat does not melt the rocks. While increased temperatures tend to melt rocks, high temperature tends to prevent melting. High pressure, it tends to prevent melting. The high pressure squeezes the rock into a solid. This solid rock of the upper mantle and the lower mantle form the largest layer of Earth. And I'm going to show you where that is right here, as you notice. Okay? Okay, so some of the last pieces of information we want to talk about is the core. As you know, the core would be one of our vocabulary words. So let's go ahead and put that on the screen so you can write it in your science journal. The core is the dense metallic center of the Earth. As shown, of course, hold on just a second, as shown in the figure above. If you imagine Earth as a hard-boiled egg, the core would be the yolk, or the middle. Earth's crust and mantle are made of rock. And so then when you think about it, why is the core made of metal? Recall that Earth, in early Earth history, the planet was much, much hotter than it is now. Materials flowed sort of like the material in the asthenosphere today. Scientists don't know how much of Earth melted at that point in history, but they do know that it was soft enough for gravity to pull the densest material down to the center. This dense material is the metals, iron, of course, being what it is. Mostly iron with small amounts of nickel and other elements. Now remember that there's a scientific use and a common use for the term nickel. The scientific use, of course, is a specific type of metal. However, the common use, which is more what we would use presently, would be a coin worth 5 cents. We're talking in this case as the scientific use. So the dense material is metal, and it's mostly iron with small amounts of nickel and other elements. The core has a liquid outer core and a solid inner core. When we talk about the outer core, if pressure is great enough to keep the lower mantle in a solid state, then how can the outer core be liquid? That's a question that I have for you. But when you think about it, the mantle and the core are made of different materials and have different melting temperatures. All materials have a different melting temperature. Not everything melts at the same temperature. Just like in the asthenosphere, the effects of temperature outweigh the effects of pressure in the outer core. Scientists have learned that the outer core is liquid by, of course, again, analyzing earthquake waves, as we've talked about in the past. The inner core is a dense ball of solid iron crystals. The pressure in the center of Earth is so high that even at temperatures of about 6,000 degrees Celsius, or about 11,000 degrees Fahrenheit, the iron is in a solid state. Because the outer core is liquid, it is not rigid, attached to the inner core. Okay, so they're not attached at all. It's not rigidly attached. It's not attached. The inner core spins a little faster than the rest of the Earth. So that is information there. The inner core actually spins faster than the rest of the Earth. Recall that Earth's inner core spins faster than Earth's outer core. This produces streams of flowing molten iron in the outer core. Earth's magnetic field is a region of magnetism produced in part, not full, but in part, by the flow of molten material in the outer core. The magnetic field acts much like a giant bar magnet. It has opposite poles. Remember, a bar magnet has a positive end and a negative end. So, for centuries, people have used compasses and Earth's magnetic field to navigate. If you have a GPS in your car, your GPS is acting on that magnetic field. The magnetic field is not completely stable, however. Over geologic time, it is proven its strengths and direction can vary. At several times in Earth's history, the direction has even reversed to where what would be normally north is south, and what is normally south is north. Earth's magnetic field protects Earth from cosmic rays and charged particles coming from the sun. Those charged particles are dangerous to humans and any kind of life. It pushes away some charged particles and traps others. The outer part of the magnetic field that interacts with these particles is called the magnetosphere. I'm going to go ahead and pull up, as you know, magnetosphere is one of our words. So I'm going to give you the definition. Please write this down in your science journal so that you will have that. To see how the shape of the magnetosphere is produced, when you take a look at our diagram, I'm going to ask a quick question, and that would be, hold on just a second, now that you've written that down, I'm going to ask a question as to, when you take a look at the blue lines right there, what does that signify? What does the blue line signify? Well, we just talked about it. If you think about what those signify, these right here, all these blue lines, if you look, Earth is in the middle, and they go like this and like this. Those blue lines surrounding Earth represent the magnetic field. Okay? And when you take a further look, this right here, that right there, that's on the outside of it, the thick back to the, that would be what we would know as the aurora borealis. Okay, the aurora borealis, which was something that we haven't talked about yet, but it's caused by the magnetic field of the Earth. The aurora forms when charged particles interact with Earth's magnetic field in the magnetosphere. That would be in this area here. So that is the reason why we see those charged particles showing up as bright colors. Okay? And that would be the end of our lesson. As a lesson review, please remember, Earth's layers include the crust, mantle, and the core. Oceanic crust is under oceans, and continental crust are made of the continents, make up the continents. The mantle is Earth's thickest layer, It includes parts of the lithosphere and the asthenosphere. And also remember, Earth's core has a liquid outer core and a solid inner core.